Good morning, everyone. Good morning. So today I'm happy to welcome the third plenary speaker, who is Meghan Clayards from McGill University. So Meghan is an associate professor at McGill University with a joint appointment in the Department of Linguistics and the School of Communication Sciences and Disorders. She's also a member of the Center for Research on Brain, Language, and Music, and an associate editor for the journal Attention, Perception, and Psychophysics. Dr. Clayards obtained a BSc in linguistics from the University of Victoria in British Columbia and a PhD in brain and cognitive sciences from the University of Rochester in Rochester, New York. She joined McGill after postdoctoral training in psychology at the University of York in the UK. And her research focuses on the structure of acoustic variability in the speech signal and the role that experience that with that structure has on the speech perception system. She also examines how individuals adapt to changes in acoustic patterns. Her recent work has examined individual differences in speech perception in both younger and older adults, as well as second language learners. So please, Meghan.
All right, good morning. Thank you for the introduction, and thank you to the organizers for inviting me. Thank you all also coming to the first talk of the day. All right. So spoken communication is an essential part of daily life. It often feels effortless, so we might think that it's relatively straightforward, but the complexity becomes clear once we maybe listen to an unfamiliar language, or even maybe we talk to somebody with an unfamiliar accent. And in fact, it's only recently that artificial communication systems have even come close to the performance of humans. And if you've ever observed a kid interacting with Siri or Alexa, you know that they still have quite a ways to go. All right, so I'm going to talk about how we recognize the sounds of speech and how we build them up into words. I'm going to show that these sounds are extremely variable in how they're pronounced. And this might present a challenge for the listener to try to identify those sounds. So I'll talk a bit about how we think the perceptual side deals with this challenge, and in particular, the role that learning plays. Okay, so in spoken communication, the message has to get from the talker to the listener, but that message is actually very variable. It has many sources of variability that affect the acoustics of the message. So here's an example of some of that variability.
Here's a story for you.
Well, here's a story for you.
Here is a story for you.
Well, here's a story for you.
Here's a story for you.
Okay, so that was all the same sentence, but spoken by people using different varieties of English. So we have some sources of variability from linguistics and social factors, also spoken by different individuals, so men and women of different ages. And that brings along some physiological factors that affect the signal. Oops. So these factors contribute to how a particular word or vowel sounds, so its acoustic properties. And the acoustic dimensions that vary are actually the same dimensions that carry the message. So the physical form of the message is shaped by these factors. And the listener somehow has to take into account these factors in order to be able to interpret the message. So that's the challenge. So this has been called the lack of invariance problem, which is a fancy way of saying the variance problem. That the physical form of the message depends on many factors. And this was considered one of the central challenges of speech perception by early researchers at Bell Labs. So today I'm going to use vowels as an example. And I know this is a diverse audience, so I'm going to start with some background and explain what formants are, and then I will talk about the various things that can affect the frequency of those formants. And then I'll talk about some ways we think listeners actually understand vowels despite all that variability, including some recent work in my lab that's focused on flexibility and adaptation. Okay, so what are vowels? So when you learn to read, you might have learned A, E, I, O, U, and sometimes Y. From a phonetic perspective, vowels are sounds that are produced with an open vocal tract. So this is a video from the University of Glasgow that shows someone talking in an MRI machine. And so just to orient you, these are the vocal folds down here that are creating the source of the sound. So that's just behind that Adam's apple. This blob here is the tongue. And I don't know how well that shows up, but this line is roughly kind of the top of the mouth running from the teeth along the palate down the back of the throat. And what I want you to pay attention to in this video is the space between the tongue and that line. And this is the column of air in the vocal tract that resonates. So I'll leave that on.
Pa, ta.
And she swallows at the end. Okay, so hopefully you can see that the vocal tract is relatively open for the vowels compared to when the tongue closes it off for the consonants. So the way that we understand how vowels are made is that it's a combination of a sound source, so the vibrating vocal folds, and a resonating column of air that filters that sound. So this is kind of analogous to the strings of a stringed instrument, so that would be the vocal folds, and the body, let's say the body of a guitar, that is the resonator that filters it. But of course, instead of being rigid like the body of guitar, the vocal tract is deformable, and a lot of what we do when we're making different vowels is we're deforming that resonator. So this is a nice example of that I took from a museum exhibit. So they created these tubes to mimic the cross-sectional area of that open space in the vocal tract for different vowel articulations. So for example, you can see for E, in the top left corner there, it's relatively narrow at the top of the tube, which represents close to the front of the mouth, and relatively open at the back, representing the pharynx close to the vocal folds. And so they made these different tubes for each of the different vowels, and then they took a sound. So this is actually it's the reed from a duck call, I believe, to mimic the vocal folds. So it sounds something like this. Okay, sounds a little bit distorted here, but that's something of an approximation of the sound that comes from the vocal folds. And then they played it inside each of those tubes. And this is what it sounds like. Okay, so not superhuman, but you should be able to roughly get the sense of the different vowels. So what this illustrates is that the different vocal tract shapes alter the sound to create the distinct vowels that we hear. And so these different vocal tract shapes, they have different resonant properties, and so they create different transfer functions. So these are two kind of cartoon examples of what that transfer function might look like for E versus ah, frequency on the bottom, and amplitude or energy along the vertical axis. So these resonant frequencies depend on two things mostly. So the first is the length of the vocal tract. So like all resonating bodies, the longer the vocal tract, the lower the formant frequency, the lower the resonant frequencies. And that's one of the sources of physiological variation between people. So people have different length vocal tracts. But the other main thing, is the cross-sectional area along the tube, like I said. So deviations from this uniform tube perturb the resonating frequencies up or down. So that means that every difference in articulation is going to produce a difference in the acoustics, in the frequencies of those resonant frequencies. And these resonant frequencies in the vocal tract we call formants in phonetics. So from now on, I'll be referring to them as formants. here are two visualizations of what those formants look like. So on the right here, we have a spectrum or fast Fourier transform showing the energy across the different frequencies, and overlaid on that is an LPC that highlights the peaks. So those peaks, those of the energy, are the formants, and I've labeled the first and second formants there. On the left is a spectrogram, so many of you might be familiar with that also. But this shows how the energy changes over time. So now we have time on the horizontal, frequency on the vertical axis, and the darkness is energy, so the dark bands represent the formants, and there, again, I've marked the first and second formants in red. So the first and second formants are the ones that are most closely linked to differences in vowel articulation. So those are the ones that we're most interested in phonetics. Okay, this is a little video that I made using a real-time spectrogram. So I couldn't do it live, but as I'm talking and producing different vowels, the spectrogram goes by, and you should be able to see how those dark bands of formants change as the vowel changes.
I-E-A-O.
Okay, you can sort of see that. Do it one more time.
I-E-A-O.
Okay, so those dark bands are changing as the shape of the vocal tract changes. All right, so hopefully now I've given you a conceptual understanding of what formants are, and now I'll talk about variability in those formants. Okay, so all of that was sort of to get you to the point where I could show this figure. So these are different vowels plotted according to their first and second formant frequencies. So first formant frequency on the bottom and second on the side. Each of the small symbols, if you can see those, is an individual vowel that's been measured. And then the ellipses represent a whole category of vowels, and they're marked with their phonetic symbols there. So these are spoken by different people, men, women, and children. And what should be sort of jumping out is how much variability there is. So how scattered those symbols are, and in fact, that many of the ellipses are overlapping. So if we think about this from the perspective of the listener who has to identify these vowels, and we'll just zoom in on these two here. So this is eh and ah. There's quite a lot of overlap. So if you imagine you're presented with one of those tokens and that overlapping part there, how would you know which vowel it is? So I'm going to talk about, I will talk about how we know, but first I'll talk about some of the sources of variability. So there are many different sources of variability. I'll start by talking about anatomical differences, which I already mentioned. So what is plotted here at the top, let's just start with the top figure, is first and second formant frequencies for the vowels of American English for a group of men and women. So it's a convention in phonetics to plot the lower numbers in the top right corner. So that means that what we can see is, so the women are plotted in blue and the men are plotted in orange. And because of the, on average, longer vocal tracts of men, all of the resonating frequencies are lower. So all of those formants are shifted up. And at the bottom, that illustrates how this could be potentially a problem. So here we have in orange productions of the vowel as in pull for men, overlaid with productions of the vowel oo as in pool for women. You can see the F1 and F2 values are very similar, even though those are different, different vowels. So this is in part due to differences in vocal tract size, but there are ways that we can normalize for that. So one of the ways is to make use of the higher formant frequencies that I said are less affected by vowel articulation. So in this case, the third formant has been used. So now these are expressed as ratios of the lower formants to that third formant, and you can see that they're much more similar. So that's taken out some of the differences between the two groups. And at the bottom there, you can see now this is pulled apart oo and a little bit better. So in terms of vocal tract normalization, information internal to the vowel, like something like this, the Formant ratios, is somewhat successful, but it's better if you actually know something about the talker's whole vowel space, so all of the vowels that they produce, and as well as how variable they are. And with that kind of information, vocal tract normalization can be more successful. There's different methods, for example, Lobanov or Neary are two common methods. And some estimates say this reduces maybe 70% of the variation between talkers and maybe most of the anatomical differences. So that's useful, but it's not going to actually get rid of all the differences between vowels. So we also have other sources that aren't due to anatomical differences. One of the big ones is going to be dialect differences. So these are, again, the vowels of American English that have been plotted. This time, each of those symbols represents one dialect group. And we also have men and women separated. So the filled circles, or the filled symbols, are men, and the open ones are women. This has already been vocal tract normalized. So these differences here are not due to anatomical differences. So we see there are still differences between men and women even after that normalization. But most importantly, we can see the variation due to dialects. So each of these ellipses is all the vowels from all those different talkers. So there's quite a bit of variability due to regional dialects. And again, these are just dialects of American English. But even beyond those dialect differences, we also see other differences. So we might think that if you kind of can account for vocal tract size or gender differences, and you can account for dialect differences, then we should be able to make people's vowels very similar. But actually, it turns out people are more different from each other than that. So this is a recent study that took a whole bunch of F1 and F2 values and kind of put them into a big pile, and then compared that to what happens if you separate it into different piles, for example, according to gender, 2 piles, and then say how different are those piles from the original pile of data. So this is a KL divergence measure. And so in blue, it's plotting the difference in bits from that whole pile if you separated it according to men and women, and they're a little bit different than the whole pile. And the gray bar there at the bottom is if you just randomly separated it into 2 bins. So you can see there's some difference that's accounted for by gender. In green is dialect, so now we make the piles according to dialect. In pink is dialect plus gender, so there's one pile just like that last figure I showed you. And you can see that that's also fairly different from just the overall variability. But what's interesting is if you instead you make the piles according to talker, so each talker is their own set of variability, then they're quite different from the average. So each of those dots is a talker. So what that means is that even when you account just for gender and dialect, people are still different from each other. Okay. So those 3 sources of variability I talked about all come from the talker, but we also get lots of variability from the phonetic context. And by that, I mean the sounds that occur before or after a particular sound. So far, all of the Formant values that I've shown you have been from words that were produced in isolation, so just a single word, and often actually in a single context, so starting with ba and ending with de, so those vowels like bed and bud. But of course, in real language, we get a lot more variability than that. We don't just hear single words. So these figures are just showing the difference between these vowels produced in a controlled context versus in a varied context. And these are all Formant values from a single talker, so this is not due to differences between talkers. So in the controlled context on the left, you can see the vowels in bed and bud are fairly separated. But once you start getting things like duck and cup and tech and web, now you get more variability and more overlap. But this is still relatively controlled, right? This is data, this happens to be from Mixtec, a language from Mexico, but it illustrates a very general property about language, is that on the top we have Formant values that are taken from lists of single words. So like what I've shown you, each of those colors is a different vowel. men on the right and women on the left. On the bottom is what happens when you measure those vowels from personal narratives, so people telling stories about themselves. So much more like what we actually encounter. And there we can see lots of variability, lots of overlap. Oops. Okay, so coming back to this overlap between these two vowels, we know that some of that's due to differences in talker. So we have men, women, and children here. So differences in their vocal tract length, differences in dialect, idiosyncratic talker differences. And it's not illustrated here, but also lots of differences from context. But yet, as human listeners, we usually are able to understand each other's vowels fairly well. So how do we achieve that? So I'm going to talk about a couple of different things that we think are important for how that works. The first one is online normalization that I've already talked about in terms of the vocal tract. But like I said, this only works somewhat well without knowing a lot about the talker. So just from the first few moments that you talk to someone, you don't have very much information about their full vowel space. And even if we can control for the vocal tract, there's still substantial variability that persists between talkers. And it suggests that instead of sort of automatically normalizing for the vocal tract, what we're doing is kind of building up an implicit cognitive model of talkers as we encounter them. So we meet somebody, we have some expectations about how their vowels probably work. As we talk to them, we get a better sense of how they use their vowels. And incidentally, the early automatic systems did some sort of explicit vocal tract normalization, but my understanding is that the most state-of-the-art systems actually don't try to explicitly model vocal tract. Instead, it's probably something that the system is learning implicitly and building something up in a similar way to what we do, perhaps. So vocal tract normalization can only be a partial solution. What's probably more important is taking advantage of structure in the variation. So some of that variation, as I said, comes from talkers, and sociophoneticians have long noticed that sort of clusters of variation go together with particular social identity. So they may be linked to a social group or a regional accent, regional dialect, or even a foreign accent. So in fact, this variation is systematically linked to talker identity. So if you know something about a talker, you probably know other things about that talker based on this social group. But there's also might be some, we saw there's these sort of idiosyncrasies of talkers, but this also might be more systematic than we previously thought. So even when it's not specifically related to social group, some recent work is showing that the way someone produces one sound may be related to how they produce other sounds. And one example of that is we recently found that talkers with higher spectral energy in an S sound also had longer consonants. So we're not exactly sure why those two things would go together, though we think it might be related to effort. And I think we need more studies to understand the sources of those covariations, so why these particular things go together in talkers, and for that we need much bigger data sets. That's something that the field is looking at right now. But it may be that talkers actually differ from each other in systematic ways. And if that's the case, listeners may be able to take advantage of this to kind of quickly tune in on how a talker is going to produce a particular sound in a particular word. Okay, and the same thing basically could be true for variation in context. So variation in context having to do with the adjacent sounds is also very systematic. In particular, influences of adjacent sounds tend to make them more similar to each other. So in this example of bed and bud, they will sound a little bit more like bead if the vowel in the next syllable is E. And there's also other kinds of patterns. For example, in English, the S in glass will be pronounced like sh when it comes before another sh. So as in glass shoes, glass shoes. tend to pronounce it as glash. This is partially language specific, so actually that kind of pattern doesn't tend to happen in French. And what we know is that listeners kind of undo some of these patterns of variation when they're listening in their native language. So we know that English listeners hear the glass in glass shoes, but that if you do something similar for French listeners, and I probably have some spelling mistakes here, but they wouldn't hear the place in place chargée, because that's not part of the pattern of their language. So we know that listeners kind of can undo the variation that's systematic, but what's interesting is that these covariations can also be used by listeners to actually identify adjacent sounds, sometimes even anticipating them before they're heard. So for example, a sound like f is very influenced by the adjacent vowels. And when you hear the f sound, you can to some extent predict what the upcoming vowel is. So David Pizzoni said, for example, stimulus variability is in fact a lawful and highly informative source of information for the perceptual process. So what we think is that actually the systematic variability is really important for the perceptual system and less a problem and more something that the system exploits. So what we think is that listeners likely have learned how the variations are linked to their sources like talkers and contexts. And as we're recognizing sounds and words and talkers, because those are all tasks that we need to do, we likely track the sources of variation and attribute that variation to its source. Okay. So this is how we think, in general, probably the perceptual system works. But even if we've learned how all this variation works together and we're tracking it and we're attributing it to its source, we're still likely to encounter new patterns that are unfamiliar. For example, talking with someone with an unfamiliar accent. And there, we think there's going to be a role for learning, so adapting. So you may have had the experience of you start talking to somebody that has maybe a regional dialect or a foreign accent you're not familiar with, and at first you have a hard time understanding them. But after a little while, you seem to be able to adapt, you can understand them better. And what we think is, in doing this, we're making use of top-down knowledge. So top-down knowledge is any kind of expectations that we can build based on our knowledge about, for example, what are the words in your language. Okay, so I have an example, a couple of examples of the power of top-down knowledge. So this is Sinewave speech. So it's a sort of a fun trick or a way to make a very degraded signal from speech. So on the bottom is a spectrogram from a sentence, and the first three formants are tracked there in red. And at the top is the Sinewave speech created from that sentence. And how it's made is that the signal is replaced by pure tones, 3 pure tones, which are modulated in both intensity and frequency to track those first 3 formants. So that's all it is these 3 tones that are modulated. So I'll play it for you, and you can see if you can understand the sentence. Okay, very clear, right? So unless you speak R2-D2, that probably didn't sound like speech. But now I'll play you the original sentence.
Once upon a time, there were 3 bears.
Okay, and now I'll play the Sinewave speech again. Okay, I'll just do it one more time.
Once upon a time, there were 3 bears.
Okay, so some of you at least have the experience of it sort of popping out once you know what it's supposed to be. So that's the power of expectation, of top-down knowledge, interpreting something that's very, very degraded and limited signal, but once you know what it is, you're able to make sense of it. So I have another similar example. This is a different kind of degradation, noise vocoded speech, or sometimes called Shannon speech. So here, what we've done is taken a sentence, divided it into a number of frequency bands, and those frequency bands have again, the amplitude modulation of the speech, but the fine structure is just replaced by white noise. So I'll play that one for you. Okay, sort of another kind of creepy robot. But that's actually the same sentence. So we'll play this again.
Once upon a time, there were 3 bears.
Okay, one more time.
Once upon a time, there were 3 bears.
Okay, for some of you, maybe it starts to pop out again. So 2 demonstrations of the kind of power of top-down knowledge, but also if we kept playing this game for a while, which we won't do, you would actually start to get better at understanding the speech without hearing the original. So you can actually learn how this strange sort of signal maps onto what you normally hear. So these top-down effects can have a powerful influence on our interpretation of what we hear, and we can use that to drive learning. So now I'm going to give you 2 examples of using our expectations to guide learning about novel accents. The first one using a knowledge of vocabulary. So by that I just mean knowing what are words and what are not actual words in the language, although they could be. So here I've plotted some stimuli according to their first and second form of frequencies, and these represent the vowels I and E. So we have words, this one, like
Dress.
So that's A, and over here,
Click.
okay, and I. But we can also have non-words, so they could be words, they just don't happen to be words in English, such as
Dress.
driss,
Clack.
clack. But we can also create things that are sort of ambiguous or intermediate between E and I. So I'm going to play those ones to you, and I want you to say, decide whether you think you hear E or I. And I'll ask you afterwards.
Dress.
One more time.
Dress.
So how many people heard E? How many people heard I? Okay, a little bit of variability, a little bit more on the S side. Let's try this one.
Click. Click.
How many people heard E? And how many people heard I? Okay, so you can see they have very similar F1 and F2 values, but we tend to hear them as if they were the real words. So we hear the one that could be dress as E, and the one that could be click as I. So this is an effect of our top-down knowledge that ambiguous sounds tend to be interpreted in a way that fits with what we know. So in this case, what are possible words? And again, this is a mechanism that can drive learning or adaptation. So in some important studies by Norris, McQueen, and Cutler, what they did was they exposed listeners to a kind of an artificial accent. So in this artificial accent, one group would hear this ambiguous sound always in words that bias towards I, and a different group would hear that ambiguous sound always in words that bias towards E. And what they found is that after this exposure, you could put this ambiguous sound in words that don't have a bias, like it could be bet or bit, and those 2 groups would hear it differently. So the group that was biased towards hearing it as I would categorize that as I, and the group biased towards hearing it as E would categorize it as E. So this may be a mechanism that we can use when we're adapting to a new accent, because in real speech, of course, we often we have real words, and they often sort of can be one thing and not another. So that can help us to sort of tune what we expect for a particular listener. And in a recent study, what we found was that this learning was actually tied to vocabulary knowledge. So listeners who had larger vocabularies learned a little bit more than those with smaller vocabularies. So we think that it might be because they have a more finely tuned expectation about what are actual words and not possible words in the language. So our knowledge of words allows us to quickly adapt to a new talker's way of pronouncing a vowel. So if they pronounce a vowel in a sort of unexpected way, but we kind of know what the word is supposed to be, that can help us adapt to that. So now I'm going to talk about a different kind of learning that I'm calling knowledge of multiple dimensions, which hopefully will become clearer. Okay, so here are two words, bet and bat, and these are their spectrograms. So we can see the F1 and F2s there. It's not so clear here, but their F1 and F2 are a little farther apart for bet. It's a bit subtle. But the thing that should be clear is that these vowels have different average durations. So the one in bat at the top there is on average longer than bet. So I'll just play you some examples.
Bat. Bet.
Okay, so they differ in both their formant frequencies and how long they are. And these are both potential cues for listeners to identify what the correct vowel is. So how can we tell whether listeners actually pay attention to those different dimensions? So what we can do is we can create stimuli that vary in both dimensions orthogonally. So that's what I'm showing here is a stimulus array. Each of those blue circles represents one potential stimulus. And they vary in the duration of the vowel, so short to long across the horizontal axis, and also in that formant cue, more like to more like. And we can play those to listeners and ask them what they hear, which is what I will do. So we can take ones where both of those cues kind of point in the same direction. So for example,
Bet.
So most of you should hear that as the gambling word.
Bat.
And most of you should hear that one as the animal. But we don't really know in that case which of those dimensions you're paying attention to. But we can also make them conflict with each other, where the duration cue is consistent with the gambling word and the formant frequency cue is consistent with the animal. So I'm going to play those and I'll ask you what you hear.
Bat.
One more time.
Bat.
So how many heard that as the animal? And how many heard that as the gambling word? Okay, a little bit of variability, good. And now this one.
Bet. Bet.
How many heard that as the animal? And how many heard that as the gambling word? Okay, a little bit more variability. All right, so on average, native listeners of English tend to hear that to go along with the formant cue. So even though the one that's long is usually heard as the gambling word. But we do know that duration still matters because we can create these stimuli where the formant cue is kind of intermediate, and then we can see if the duration has an effect. So let's see how this one sounds.
Bet. Bet.
So how many hear that as the gambling word? And how many as the animal? Okay. And
Bet. Bet.
so how many hear that as the gambling word? And how many as the animal? You're less sure now, but okay. So we are seeing that goes roughly with the duration. So these experiments, I think, are very boring for the participants. But what we do if we ask a whole group of native listeners what they hear is we can get data like this. So this is color-coded according to their responses, with red being the animal and blue being the gambling. And what we can see here is that the color mostly changes top to bottom. So it's mostly changing according to the formant cue. There's a little bit of a change left to right, having to do with duration, especially if you look at that ambiguous case in the middle. You can see it changes a little bit left to right. So we actually, native English listeners mostly rely on formants, but also duration to some extent. So this was actually part of a longitudinal study of Korean learners of English who had come to Montreal to learn English. And we chose this vowel because this is actually a difficult contrast for many learners of English. So probably many of you in the audience may have found these a little bit hard to tell apart. So learners from whose first language is Korean, German, Spanish, Mandarin often find these vowels particularly difficult in English. And so you can see here in the data from the Korean learners that after 1 year, they're not looking quite like the native listeners, and that color is changing a little bit more left to right, so a little bit more of an effect of duration than it is for the native listeners. And it's particularly clear if you look at these conflicting cases where the native listeners are pretty consistent in their categorization, and it goes with the Formant cue, but the Korean listeners are much closer to 50-50 in those cases. So Korean learners of English, and also learners from many other language backgrounds, actually use duration more, both in listening and in talking. So what this can mean is that if you encounter Korean accented English, these vowels are going to sound a little bit different, and they may vary more in duration and less in the formant frequency than you would expect for a native speaker. So what if a talker uses the wrong dimension? So we simulated a foreign accent that mostly uses duration instead of formants for these vowels, and we wanted to know whether listeners would start to use the duration more. So again, these are two stimulus arrays. On the left is our simulated foreign accent. So this was the exposure phase. And here we gave them stimuli that were mostly in that intermediate range for the formant cue, but varied in duration, so both short and long. And we compared that to a baseline condition where they had the full range of formant values and also short and long again. And we're specifically going to look at the stimuli that are represented by the red square and the blue triangle. So they occur both in baseline and exposure. And those are intermediate for the formant cue, and they only vary in duration. So there we should see how much of an effect the duration of the vowel has on listeners' categorization. So now I'm plotting the proportion of A responses. So numbers closest to 1 are more bat or animal responses, and numbers closer to 0 are more bet or gambling responses. And what we can see in the two baseline blocks is that when the vowel is longer, so that's the blue triangle, we get more bat responses, consistent with that being on average a longer vowel. And when it's shorter, we get more bet responses. The question is, does the effective vowel duration increase during the exposure block? So when they're exposed to this artificial accent where formant is not actually very informative, you can kind of tell already from those lines that they do. So the difference between the red and the blue symbol is much bigger. Their responses are more influenced by duration during the exposure block. This is relatively rapid adaptation because the entire exposure block lasts about 15 minutes. And you can also see that when we give them the second baseline, they very quickly go back to their regular behavior. So this is something that seems to be sort of rapidly turned on, but when they encounter something that's more like they normally experience, they go back to their normal behavior. So they don't leave the lab with the wrong ideas about how to understand vowels. So what we found is that when listening to a simulated foreign accent, listeners increase their reliance on a previously less important dimension. And that may be one way that we actually adapt to these differences between talkers. So this is just two examples of rapid learning, but this has been shown many times in many different kinds of ways that people adapt rapidly. We don't know exactly how much exposure is needed, but maybe a conservative estimate would be like 10 or 20 minutes, or maybe 50 to 100 trials. It might be even faster than that. And we think that what listeners are doing is they're using their knowledge of what's expected and what's unexpected to drive this learning. And this might be part of what facilitates adaptation to novel talkers, including unfamiliar accents. So one thing that we've noticed in this data, and one thing that we're interested in, is that there does seem to be individual variability in how quickly or how much people adapt. And we don't yet know why these differences exist. Some factors that might be involved include things like vocabulary knowledge. So we saw that in that first experiment, bigger vocabularies led to more learning. But vocabulary, of course, is just one kind of knowledge that you have about your language. So maybe language knowledge more generally is one of the factors. But we've also think there might be a role for cognitive control. So cognitive control refers to a variety of executive function measures or aspects of our cognition that control things like attention. And in our case, we looked at how well people can ignore distracting information. And so we did that in this experiment. And it's a little bit hard to read this figure, but this is showing differences between individuals according to our cognitive control measure. So on the left is those who performed better on that measure or had kind of stronger cognitive control. And on the right, those that were poor. And kind of unexpectedly, the ones with the poor cognitive control actually learned more. So it's not what we were predicting. But we think it might possibly have to do with focus of attention. So a stronger cognitive control, better ability to ignore distractors in these tasks might be related to having a relatively narrow focus of attention. Whereas having a sort of poor, or that's not really the right word, but less cognitive control in these tasks might relate to having a broader focus of attention. And this broader focus of attention might allow some of this kind of implicit learning to different patterns that come up. So this should be interpreted with caution because we did not predict this, and we definitely need to look into this more. But it's something that's sort of come up in some different studies, so it's something that we're following up with. These individual differences in learning are sort of exacerbated when we look at second language learning, which is of course a very difficult task. And so this is, these are 3 individual learners from our longitudinal study of Korean learners. And you can see that compared to the group data that I showed you earlier, they're actually very different from each other. So we have this one on the right here who's mostly using duration. So the color is mostly changing. The one in the middle is mostly using duration. So the color is changing mostly left to right. And on the left, we have one who's mostly using Formant. So similar to native listeners. And then this one on the far right kind of seems to be doing both, but in a way that's a bit different from native listeners. And we know from some other data that this one is our more sort of successful learner, seem to be better able to recognize at least the vowels. And we're interested in these differences. They're relatively large differences. We don't yet know why or what drives these differences. But we did notice that these differences were already detectable in some of our earliest measures of them, so after just a few months in Montreal. So we think there might be something about these learners where they're either quickly able to hone in on the right dimensions, or it's just a little bit easier for them to pay attention to these dimensions. All right. So what I've hopefully shown you today is that acoustic variability is ubiquitous in speech production. There's many sources of variability, and those sources of variability affect exactly those dimensions that are relevant for identifying particular sounds. And they can come from social factors, for example, regional dialect, linguistic factors such as the adjacent sounds, physiological factors like vocal tract length. But that variation is largely systematic and structured. And we think that listeners use the variation to identify sounds and words and talkers by their effects on each other. And although early on people thought maybe we had to sort of remove this variability to get at the message, now the understanding is that actually you need to be able to identify the talker as much as you need to be able to identify the word. And so those things actually sort of have to be taken into account together to identify both of them at the same time. Work is ongoing to uncover some of the structure in this variability, particularly as it relates to differences between talkers. But we think that some idiosyncratic variation does likely require some online adaptation or variation that you're just not familiar with. And what we know is that listeners are very flexible and they actually adapt very rapidly. And ongoing work in my lab and in other labs is investigating differences in plasticity among individuals or how easily or quickly they seem to adapt. So thank you all. Thank you again to the organizers for the invitation, and I'd also like to thank my collaborators and sponsors.
Thank you, Meghan. We have time for questions.
What's your opinion on Yanni or Laurel?
Yanni Laurel. So I can't remember, but I know that there was a discussion going around about how that works, and I don't remember how it works. I don't have an opinion, and I don't remember which one that I hear. I think
I've heard of Yanni all the time.
I also heard one all the time, but I don't remember which one it was. Yeah.
Hi, thank you for your talk. What about music training? Have you all looked into that, whether or not that affects the plasticity?
So I haven't looked at music training, but others have. And it is something that people often actually control because those who have extensive music training seem to be particularly good at certain aspects of perception, especially to do with pitch or tone. I don't know if anyone has looked at plasticity, but probably they have, and I just can't think of it right now. But I know that some studies, for example, have looked at English learners learning Mandarin tones, and there you absolutely have to control for music training because musicians have an advantage there. Yeah.
Hello,
Hi.
interesting talk. I was wondering whether you did some work with people with hearing loss, because in the literature we sometimes hear that they might compensate for the hearing loss using duration. So I was wondering whether in the duration Formant trade-off, because they might not have access to F2 anyway. So.
Yeah, yeah, that's really interesting. So I haven't looked at hearing loss. I do know of one study that showed that some people with hearing loss actually sort of weren't taking advantage of the kinds of cues that were preserved as much as they should. But you would think that if there's this kind of plasticity, there would be some kind of adaptation to that. But I don't know that literature that well, unfortunately.
Yes. Thank you for the talk. I'm wondering how can we use your work to improve the intelligibility tests?
What do you mean by improve intelligibility tests?
So far there is standards to test intelligibility, especially when we use communication headsets. But we know that when we use those type of devices, there is some type of filtering of information. And so the challenge is to make sure that there is intelligibility, even if there is some changes in the accent, in the way how people are talking. And those standards so far are not very built like a stone. There is many tangents, and what I see as per your presentation, maybe there is a possibility to tweak or to propose something that adapts to the way how people speak, to assess intelligibility or device to make sure that communication via that device goes clearly and so on.
Okay, so I'm actually starting a project with Rachel Borsehal, which is looking at a little bit of how we could maybe train listeners a little bit to some adverse conditions, maybe harness some of this plasticity. And one thing that we know about this kind of learning is that it's definitely really enhanced by having this kind of top-down knowledge. So I think one possibility, if you want to work on the side of the listener, is to potentially train them with the real conditions, with the device, but have some feedback. So for example, it's been shown that having subtitles in the language that you're hearing can help you learn something about that accent. So potentially having, let's say, the text of what the person is saying could be something that could help boost the sort of training or plasticity for the listener. In terms of intelligibility testing, there I'm less sure, but I think we would want to have the conditions match as well as possible. So matching, the language that it's being used in, for example, you would want to do that in testing the intelligibility. But I mean, the good thing is that listeners are very plastic and they are good at using top-down knowledge. Of course, we also know that takes some effort. So even this adaptation to a new talker, we know takes effort. And that's, I think, one of the challenges of the hearing and noise or these kinds of conditions is that although you can achieve a certain level of performance, it's effortful. And so things we can do to reduce that effort are good. I don't have good solutions other than maybe some training conditions that could help people sort of pre-adapt sort of under ideal training conditions potentially. Hi, Rochelle.
Hey, Megan. Thanks for your talk. I had a question about, you said that Korean non-natives use duration. Is it strictly because they're Korean and maybe that's what they use in their own language to distinguish? Or is this any non-native will use duration more than Formant?
Right, so people often ask exactly that question. And no, so Korean doesn't use duration more than English for distinguishing vowels. And in fact, we get listeners from many different language backgrounds have difficulty with these vowels, and they all tend to use duration more. So it's kind of an interesting puzzle. We're not exactly sure. So we definitely know that the reason that particular language backgrounds have trouble with these particular vowels is that these vowels are actually a little bit more overlapping even when you account for all the sources of variability. So the Formant differences are subtle, and in those languages, there isn't similar types of vowels. So there isn't a vowel like a in Korean or in German, and that's why those particular listeners have difficulty with those vowels. We don't know exactly why they go with duration, other than a general sense that there must be something salient about duration. You can kind of hear it. And we know that duration is actually super important for all kinds of things in speech. So it helps us get the rhythm. Lots of aspects of consonants are actually dependent on duration. The prosody is really important. So we know that everybody has to use duration in understanding speech, so it's something you can kind of turn to when something is more difficult. And it turns out that these things are somewhat separated by duration. So that's sort of the sense that it must be that duration is kind of easy to use, and the formants in this case are hard to use. And so learners from a background where they're not used to those particular vowels will rely on duration.
More questions? Well, thank you.
Thank you.